All right. So let's just kind of review. We had started in on chapter 21. First, we quickly did chapter 20 last week on carboxylic acids and nitriles. And then we moved on to these carboxylic acid derivatives. All right. The first thing we did was nomenclature of our carboxylic acid derivatives. All right, so just to remind us, our carboxylic acids, we had this oic acid suffix, and our nitriles had our suffix nitrile. And then we introduced our carboxylic acid derivatives. There were three that we learned how to name. These acyl halides, which use the suffix oil, and then the name of the halide. Amides, which are kind of like nitriles. The suffix is just the name of the functional group, amide. And then lastly, the esters. These are sort of the most complicated because they have that alkyl group that goes out front of the name and then followed by the parent chain with the suffix -ate. All right, so then to finish our discussion of our nomenclature here, let's update that priority list that we've been building of our different functional groups. Remember, we were ranking our functional groups from highest priority to lowest priority. All right. All of our carboxylic acid derivatives, they do have prefix versions for when they are not the highest priority group, but they're kind of a pain in the ass to work with. And so honestly, what we're going to update our priority list is to just put at the very top of this priority list all carboxylic acid derivatives. All right, they're going to beat anything else, any of these other functional groups that we have learned about. All right, but then what do we do when we have a carboxylic acid and, for example, an amide in the same molecule? We're not going to deal with those special case scenarios. All right. These are this is the priority list we're going to work with, and we're just going to say that all of our carboxylic acid derivatives sit at the top of this priority list. The other thing that we want to do to finish this off is to take a look at the special names. So what do I mean by that? Remember, for our carboxylic acid, we said that a 2-carbon carboxylic acid is not ethanoic acid, but has what name? Acetic acid. And this is considered the IUPAC name of this molecule. So these 2-carbon carbonyl groups always have these special names. So for example, if we had a 2-carbon acyl chloride, this again, you would think it would be ethanoyl chloride, but it's got its own special name. This is acetyl chloride. All right, if we have a 2-carbon amide, it's not ethanamide, it's acetamide. All right, and then lastly, if we have an ester that has 2 carbons. I guess we can just look at a specific example here. All right, on this half of the molecule, these 2 carbons, there's nothing special about that. There's no carbonyl group there, so this would just be ethyl. But on the other side, those 2 carbons with that carbonyl group is that special name, so this will be ethyl acetate. All right, 2 carbon carbonyls get these special names that we just got to know. Cool. All right. So then we talked about how we can rank these different, rank these carboxylic acid derivatives from most reactive to least reactive. Our acyl chlorides sit at the very top, followed by acid anhydrides, followed by those thioesters. We then have an oxygen in that position there attached to that carbonyl carbon for both a carboxylic acid and an ester. We lump these 2 together. And then our least reactive are our amides. And we talked about why this ranking is that way is because if we look at these leaving groups here, these are ranked from the best leaving groups to the worst leaving groups, right? So that explains the reactivity that we see here. All right, so then if we want to start with our most reactive, we can turn it into any one of our other functional groups. Okay. Can turn it into a acid anhydride. Or a thioester. Or a regular ester. Carboxylic acid, or an amide, right, into any one of our other carboxylic acid derivatives. Okay, and we said that these acyl chlorides are so reactive that you really don't even need to use the strong nucleophile for each one of your functional groups that you're starting out. You can use the weak nucleophile. So for my amide, I would just use ammonia. What about my carboxylic acid? I would use just water. What about an an ester? So the strong nucleophile would be that alkoxide ion, but that's overkill. We can just use, what is this going to be when I put an H here? An alcohol. Our thioester, we can leave this as an R group as well. RSH. All right, the one exception here is if we're trying to make an acid anhydride, we would want to use the carboxylate ion instead of a carboxylic acid. All right, so that's how we can convert from something more reactive to something less reactive within our carboxylic acid derivative series. All right. We want to look at then other reactions of these acyl halides. Okay. So these are going to be reactions where we're starting with one of these acyl halides, but we're not converting into one of our carboxylic acid derivatives. We're just treating it with another reagent. And these are going to be pretty familiar here. All right, so our first one is going to be what happens when we take our acyl halide and we combine it with a Grignard. All right, we know that Grignards like to play the role of what? Nucleophiles or electrophiles? Nucleophiles, and they're going to attack that electrophilic carbonyl carbon. And so just like we've seen before, it's exactly what's going to happen. Our nucleophile attacks that carbonyl carbon, kicks up that leaving group pair of electrons, and this creates this intermediate that we have a fancy name for, our tetrahedral intermediate. So I've added on my 1, 2, 3 carbons of my Grignard to my 1, 2 carbons of my electrophile, creating this tetrahedral intermediate. What's going to happen to this tetrahedral intermediate? Is it going to just stay like it is? Is it stuck? No. What are we going to do? We can kick off that leaving group, right? These are why these carboxylic acid derivatives are kind of put into their own category, because they have these leaving groups on there. All right, and so at this point we have, what new functional group did we just create? A ketone. But what do we know about ketones and Grignards? They react with one another. So we've created this intermediate ketone here. We're not going to be able to isolate this thing. It's just immediately going to go and react with a second molecule of our Grignard and create an alcohol product. All right, so now we have this second reaction, a second round here, where our Grignard attacks that newly formed carbonyl carbon. Now we get another tetrahedral intermediate. All right, but what's different about this tetrahedral intermediate is now it is stuck. Now there's no good leaving group that can be kicked off here. The only thing that we can do is that second acidic workup step where we protonate that alkoxide ion, creating an alcohol. All right, I guess if I'm going to be good and finish my mechanism here, let's do that last proton transfer step. And that gets me my alcohol product. All right, so if we want to summarize our reaction of an acyl chloride, or any acyl halide really, with our MgBr, we don't just have one alkyl group added, but 2 of those new R groups are put on. Okay, we have another reagent that is very similar to our Grignard, another organometallic reagent that will create new carbon-carbon bonds, but it's considered a weaker nucleophile than the Grignard. Those are the Gilmans. All right, and that weaker Gilman will only put one R group on there, leaving that carbonyl group intact. And we've kind of seen this before. Grignard and Gilman are very analogous reagents, but Grignards are stronger. Gilmans aren't as good of a nucleophile, so it'll stop at that ketone step. Okay, so then lastly, we're going to react this with another good nucleophile that we're used to seeing here, our lithium aluminum hydride. Remember, these have these nucleophilic hydrogens. All right, let's see if we can't figure out what our products would be. Okay, again, our hydride has this nucleophilic hydrogen. Hydrogen's very rarely a nucleophile, except in these hydrides. It's going to attack our electrophilic carbonyl carbon, kicking that pair of electrons up. This again creates that tetrahedral intermediate. All right. But now instead of an alkyl group in our tetrahedral intermediate, we have a hydrogen, right? So these have very similar mechanisms to that of a Grignard. You're just adding a hydrogen on there instead of an alkyl group. All right, so everybody take a second. See if you can't finish this off for me. What is going to be the product of this reaction here? All right, my tetrahedral intermediate is not stuck. It's going to kick off that leaving group. Giving me an aldehyde. But what do we know about aldehydes and lithium aluminum hydride? They're going to react. So same thing, we're going to have one more round here of reaction. Another aluminum hydride. Whoops. Realize I got too many over here. That nucleophilic hydrogen is going to attack that electrophilic carbonyl carbon, creating another tetrahedral intermediate. But this time my tetrahedral intermediate is stuck. So the only thing we can do is follow it up with that acidic workup, creating that primary alcohol product. So just like we saw with our Grignards, there's going to be one reaction that occurs that reforms that carbonyl group. But these reagents react with carbonyl groups, so it's going to react a second time, giving you a fully reduced primary alcohol. All right. And much like our Grignard reaction, we have a weaker version of this that will stop after just one addition. And that is that DIBA business. Acid? You don't need acid. No, yes. All right, this will, in effect, chop off that electronegative atom, leaving you with an aldehyde. We called lithium aluminum hydride our strong reducing agent, and DIBA is our weak reducing agent. All right. Cool. So let's move on to our next carboxylic acid derivative, these acid anhydrides. These acid anhydrides are more reactive than our other carboxylic acid derivatives, with the exception of those acyl chlorides or acyl halides. Okay, and these are highly reactive. So they are very easily converted into thioesters, regular esters, carboxylic acids, and amides. All right. And again, they are very highly reactive. You don't need to use the strong nucleophile version. You can use your weak nucleophile version. So everybody take a second and fill in our table here. All right, so my amine, I would just use ammonia. My carboxylic acid, again, I would just use water. My ester, I would just use an alcohol. And my thioester, I would use a thiol. Okay, let's just take a look at one of these reactions here. We'll just take a look at the reaction involving water and specifically looking at our mechanism. Okay, this will create a carboxylic acid But let's see if we can finish off this mechanism here. So what role is water going to play in this reaction? Our nucleophile. And what's going to be our electrophile? That carbonyl carbon. Take your pick, either one. This will form our tetrahedral intermediate. All right, but when this tetrahedral intermediate forms, we got a good leaving group here. So when this leaving group gets kicked off, what is my leaving group here? Yeah, a deprotonated carboxylic acid, which we call a carboxylate ion. All right, so we're going to get both a carboxylic acid and that carboxylate ion as our product. One of them is formed with that water that's acting as a nucleophile, and the other is my carboxylic acid leaving group, carboxylate leaving group that got kicked off in this reaction here. All right, if we're being good in our mechanism, there's one more deprotonation step that we're going to have to do. And since we got water in the mix here, water is going to be our proton acceptor. All right, so importantly with these acid anhydrides, our leaving group is a carboxylate ion. And why are carboxylate ions good leaving groups? Because they're resonance stabilized. Okay, so like our acid anhydrides, our like our acyl halides, our acid anhydrides can be easily converted to those less reactive functional groups by adding in the proper nucleophile. All right, so now let's go back to our carboxylic acid reactivity list. And we're going to focus on these two here in the middle, the carboxylic acid and the ester. And we ranked these as equal here because they both have oxygen in that position of that more electronegative atom. All right? So first of all, carboxylic acids and esters. Okay, so again, we classify these as being equally reactive on that carboxylic acid derivative series. Okay? So carboxylic acids and esters can be converted using the following reactions. A carboxylic acid plus an alcohol gives an ester. And water. Okay? This is what we would call a dynamic equilibrium. Meaning one side of this reaction is not super favored over the other side. They're pretty balanced out energy-wise. Okay? So what that means is we can take advantage of that and Le Chatelier's principle to tune this reaction to go in one direction or the other. All right? So if we have an excess of our reactant, excess alcohol or carboxylic acid, that'll push the reaction in favor of our ester product. Or if we take an ester and we introduce it to an aqueous environment, an environment with lots of water molecules floating around, it's going to push the reaction in the other direction. And we're going to hydrolyze that ester into a carboxylic acid and an alcohol. So excess water, aka aqueous conditions. This will favor our reactant side or our hydrolyzed ester. Okay, and we've done this in the lab. We've taken carboxylic acids and alcohols and used them to make esters. If we took that ester and added it into an aqueous environment, it would hydrolyze back into an alcohol and a carboxylic acid. So we can kind of tune this reaction in various ways. The reaction all by itself is quite slow, so we will catalyze this reaction because it's not really strongly favoring one side or the other. So we catalyze this reaction using acidic conditions. So then let's do our mechanism here. All right. If we're starting with a carboxylic acid and our alcohol, again, our carbonyl carbon is going to play the role of an electrophile, get attacked by that nucleophilic oxygen of our alcohol. All right, so if we did this as our first step here, we would get this tetrahedral intermediate. Okay, what's wrong with this tetrahedral intermediate? Well, there's nothing wrong with the tetrahedral intermediate. What's wrong with it existing under my acidic conditions here? Got that negative charge. All right, so this can't be the first step. How do we manage our charges? I tried this out. That was a natural kind of first step to think of, but I got this negative charge. So what am I going to do up here first that's going to prevent that negative charge from forming? I'm going to protonate that oxygen. Absolutely. We use these proton transfer steps to help manage our charges, and that's exactly what we're going to do here. We're first going to protonate that oxygen. Now, when my tetrahedral intermediate forms, it will be neutral instead of being negatively charged. So take a second and see if you can't finish off this mechanism. We call these Fischer esterification reactions, these acid-catalyzed ester formation reactions. So now when my nucleophile attacks and I form that tetrahedral intermediate, it won't have any negative charges. All right, so if I say, okay, I have a good leaving group, let's bring this pair of electrons back down here and kick this off. What would be kicked off as my leaving group is the hydroxide ion. Is that allowed under basic conditions? No, so under acidic conditions, thank you. No, so what are we going to have to do? We're going to have to do another proton transfer step. The lazy man's way to do this is to notice that we need to do a proton transfer step to add one to this OH group and to lose one from this oxygen. So we can kind of kill two birds with one stone. Do this internal proton transfer. If you broke it up into two steps, that's fine. All right, now when I reform my carbon-oxygen double bond and kick off that leaving group, it will leave as water, a neutral molecule. All right, and then I have just one more proton transfer step to go to deprotonate that carbonyl oxygen. All right, and as we said, this reaction is very much so in a dynamic equilibrium. So if instead we were starting out with our ester and our water under these same acidic conditions, that ester would be hydrolyzed to form our carboxylic acid and our alcohol. All right, we don't have to draw the full reverse mechanism here, but let's just note, if we wanted to do our mechanism but in reverse, all of our intermediates stay the same. All right, we would just have to redraw in our arrows. Right, so if instead I wanted to do this in the reverse direction here, I would be protonating that ester's carbonyl oxygen. I would have water attacking the ester's carbonyl carbon to form our tetrahedral intermediate. All these intermediates would be the same. We would just be having to redraw our arrows to go in the reverse direction. Okay, so dynamic equilibrium, let's say specifically under acidic conditions. If we took this same reaction but chose different conditions, remember all your catalyst does is speed up your reaction here. So you wouldn't think that your catalyst would have a big impact on the direction of our reaction. But if we did this same reaction under basic conditions, it only goes one direction, all right? And that direction is towards our carboxylic acid, towards our hydrolysis of our ester. Okay, so under basic conditions, only ester hydrolysis. All right, so why? Well, let's start with our ester. And let's add in our hydroxide ion. That hydroxide ion is both a base but also a good nucleophile. It can attack that electrophilic carbonyl carbon, creating that tetrahedral intermediate. Oops. All right, my tetrahedral intermediate is going to reform that carbonyl group and kick off that leaving group. Because this is basic conditions, I can get away with that alkoxide leaving group, that negatively charged alkoxide ion as my leaving group. And I have my carboxylic acid. All right, but your carboxylic acid, here's the shtick though. It doesn't stop here. What's going to happen to this carboxylic acid in basic conditions? Carboxylic acid, going to play the role of an acid. So my base is going to deprotonate that carboxylic acid, leaving me with that carboxylate ion. All right, and importantly, why can't this reaction go in the reverse direction? Because my carboxylate ion, that carbonyl carbon, is no longer an electrophile. That negatively charged oxygen has a bunch of electron density that it's going to spread through resonance to that other oxygen. So this is no longer going to be an electrophile. It's no longer left relatively electron deficient because of this carboxylate ion that's formed here, because of that extra negative charge that's on there, right? So under basic conditions, your carboxylic acid is going to be deprotonated, leaving it no longer a electrophilic carbon. All right, so that very first important reaction to remember with carboxylic acids is its role as an acid. And so because of that, because it's going to lose that proton, its carbonyl carbon will no longer be able to play the role of an electrophile. All right, so this reaction here only goes in the direction of hydrolysis. Okay, so we've spent a lot of time talking about converting less reactive groups into more reactive groups. And if we look on our spectrum here, these are both considered to be more reactive than an amide. So I should be able to convert a carboxylic acid into an amide. All right, so if we take our carboxylic acid, and we add in an amine, this reaction should give us an amide. Right? If that were to be the case, then my carboxylic acid was playing the role of an electrophile, and my amine playing the role of a nucleophile. All right, but this reaction does not occur. Why not? Carboxylic acids, they are electrophiles, and amines are nucleophiles. But carboxylic acids are also acids. And what do we know about amines? They are bases. So you are not going to have any sort of a nucleophilic substitution reaction. You're just going to have a simple acid-base reaction where you're left with a deprotonated carboxylic acid and a protonated amine. All right, and the problem is that after this proton transfer has occurred, as we just discussed, your carboxylic acid is no longer an electrophile. Likewise, your amine, now that it's donated that pair of electrons to that proton, it no longer has a lone pair that can do any attacking. So likewise, we kind of ruined our nucleophile as well. We can do this reaction here, but we need to add in what's called DCC in order for that conversion to happen. Okay, DCC, I'll draw out the structure. All right, the important feature here in this molecule is this nitrogen-carbon-nitrogen bond here. This will attack your carboxylic acid and prevents proton donation. So it kind of gunks up that hydroxyl group on your carboxylic acid so that it can't deprotonate and you don't have an acid-base reaction. You instead have your expected nucleophilic addition or substitution reaction. All right, so without that special catalyst, you just have an acid-base reaction. But with that special catalyst, that DCC, you will get your expected nucleophilic substitution reaction, converting your carboxylic acid to an amide. Okay. Since an ester is not an acid, esters will combine with amines rather, to create amides. Again, converting our more reactive functional group into our less reactive functional group. All right, practically speaking though, this reaction is very slow. And so practically speaking, it's easier to convert your ester into a carboxylic acid and do the previous reaction that we learned. Okay. We talked about, cool, so converting more reactive functional groups into less reactive functional groups. This would be our last one here. Our ester can be converted into an amide by adding an amine. Practically speaking, a very slow reaction. So typically you would first convert this to a carboxylic acid, and then you could convert to an amide. All right. We talked about these reducing agents, these reduction reactions for our acyl chloride. All right, see if you can't remember what the product of those reduction reactions are. Okay, so remember these are going to create primary alcohols. We would get the same product if we used a 2-carbon acid anhydride. A carboxylic acid, or an ester. All of these would be reduced to that same primary alcohol by that strong reducing agent, lithium aluminum hydride. All right, the odd one, the odd man out here is our amides. Right, notice that in all of these reactions here, we hung on to that oxygen. But here, nitrogen is a way worse leaving group than an oxygen. You're not going to be able to knock that nitrogen off of there. And so instead, these will reduce to primary amines using that same lithium aluminum hydride. All right, you're not going to be able to knock that nitrogen off of that formerly carbonyl carbon when you form that tetrahedral intermediate, because nitrogen is a very bad leaving group. Okay. Likewise, we talked about how these acyl chlorides will react with Grignards. Putting 2 new R groups on there. Okay. We would get this same product if we started with some of our other carboxylic acid derivatives. If we started out with an acid anhydride, same product when treated with a Grignard. Or if we started out with an ester, we would get that same product when treated with a Grignard. All right, all 3 of these would lead to that same not primary alcohol, same alcohol product, all right? Previously, we also threw carboxylic acids into this same bin. Everybody take a second and tell me what my product of my reaction would be if I took a carboxylic acid and treated it with a Grignard. What are we going to get? We're not going to have any nucleophilic substitution. Our Grignard is a very good nucleophile, but it's also a strong base, and so what we will see is a simple acid-base reaction where we deprotonate our carboxylic acid and ruin our Grignard. Okay, we just add that proton on in place of that magnesium, creating just an alkane. All right, so you kind of ruin your Grignard that way, creating your carboxylate. Let's just note that we had talked about reactions of nitriles with Grignards as well. Okay. These sort of start off how you would expect, with that carbon playing the role, that nitrile carbon playing the role of the electrophile. You get these imine ion intermediates. But when you do that second acidic workup step, your imine under this aqueous conditions isn't going to survive. I guess one of these is an R group. And instead is going to be replaced by a carbonyl group. And you see something fairly similar when you start out with a amide and treat it with a Grignard. You also get a ketone. All right, so again, summarizing all of our carboxylic acid derivatives reactions with Grignards. Many of them will react at that electrophilic carbonyl carbon, forming first a ketone, but then ketones also react, so you end up getting two R groups on there. If you have a carboxylic acid, it just straight up doesn't work with the Grignard. There would be like literally no reason why you would do that reaction there. Like, why are you trying to deprotonate a carboxylic acid with a Grignard? It's just a waste, right? So this is just showing that this reaction does not produce that same nucleophilic substitution product that you would expect. All right, and then if we have one of these nitrogen-containing groups, either our nitriles or our amides, they will react to form ketones. Cool. All right. So that does sort of it for our carboxylic acid derivatives chapter. Let's just summarize all of this stuff here. Or rather, let's just practice this stuff. All right, so if we look here, we have 1, 2, 3 reactions that are all about converting something more reactive to something less reactive in our carboxylic acid derivative series. So in order to convert an acyl chloride into an acid anhydride, I need to add this component here, my carboxylate. All right, and that will be my nucleophile attacking that electrophilic carbonyl carbon, which will then kick off that good leaving group, leaving me with my acid anhydride. A carboxylic acid is even less reactive than an acid anhydride, so we can convert that. And our acid anhydrides are quite reactive. We can use just the weak nucleophile water. Okay, and then an acid anhydride into an amide, again converting a more reactive to a less reactive functional group. So I'm just going to add that neutral version of that substituted group. Okay. All right, so then in this first reaction over here on the left, we're creating that acid that acyl chloride using this SOCl2 thionyl chloride. What gets converted into a acyl chloride? Carboxylic acid. So this was our one way, and it doesn't use something simple, it uses something fancy, one of our fancy reagents. But this was that one way that we had to go back in our reactivity series, is converting that carboxylic acid to a acyl chloride using SOCl2, thionyl chloride. All right, and then this one I wanted to put next to it because it also uses that thionyl chloride, but in a really, really different way. In my mind, I have like a little star next to this particular reaction because it does not do what you would expect it to do necessarily. This is a way that we can convert an amide into a nitrile. This was one of our ways of creating a nitrile. Very different than what it's doing over here. And the one makes sense, the other one doesn't. So again, I have a little asterisk next to this in my brain, like, wow, this is a weird one. Gotta just remember. Okay. And then if I want to take that amide, actually it would work no matter which one of these we would do. We could start with our nitrile or our amide, and we could convert to a ketone that has more carbons, creating new carbon-carbon bonds using a Grignard. In this case, it would have to be a 1, 2, 3 carbon Grignard here. And then the second step is that acidic workup step. Okay, and both nitriles and amides get converted to ketones when treated with Grignards. Cool. What's up?
So does the Gilman not work for this one?
The Gilman for what? For when you're starting out with your acyl chloride, you can use a Gilman. You can't use a Gilman with an amide. Yep. So we're going to kind of just, I think you can also treat an acid anhydride with a Gilman, but we're going to just leave it with the acyl chlorides. Cool. All right, break. We will pick this up next time.